Hello everyone and welcome to my channel. In this lesson I will give you top 5 reasons that I think they are important to learn assembly language. So here is the list. Top 5 reasons to learn assembly language. First reason, and very important one, is that you have direct access to the hardware. So you can do a lot of things having direct access to the hardware, and also I want to say here that you might have some special instructions that only in assembly language are working. Reason number 2, now you will understand better how the processor and the memory works. So this you will see with experience when you are writing assembler programs, and you will understand better how your microcontroller works. Reason number 3, if you want to create compilers, you need to learn assembler. So here's a picture of a compiler design. When the compilation is started, your code will be transformed in assembly code, and after that to machine code. Reason number 4, low-level debugging for optimized code. Most of the projects have the code optimization turned on. What this means? It means that the compiler will optimize some parts of your code. So if you encounter a bug, let's say you created a counter to use it for a timer, for a delay, or a bounce counter, and you will see that the counter doesn't work. So maybe you forgot the volatile keyword, maybe not. You can look inside the assembly code during your debug session, and you will see exactly what is happening with one line below the optimization or after. And now reason number 5, reverse engineering. Here I want to recommend a book. So the book that I want to recommend is this one, Reversing Secrets of Reverse Engineering. You'll not learn reverse engineering for ARM microcontrollers, but you'll understand the techniques, what is legal, what not, and many other aspects of reverse engineering. So this is a book that I recommend. Now there is also a reason number 6. Reason number 6 says that you'll appreciate high-level languages. Not only that you will appreciate them, you will also better understand what will happen under the hood. So you will be a better programmer. Now let's create an example of an assembly program in which we want to turn on the green LED of the STM32 Nucleo board. So I'm going to show you what board I have. Here is the board that I have. It's connected to the PC, and we want to turn on the LED from the board, which is the green LED. For this, I have already written a program, so I will go faster because you will find a file inside Git. We will only create one file, and let's get started. First project, new microvision project, somewhere on your disk. Give it a name to the project. Search for the microcontroller that it is on the board. For me, it's this one. I will not select anything from here, so I'm going to press OK. So here is an empty project. I will rename this target one to STM32. I will put here assembly source, and I'm going to create an assembly file. For this, right click, add new item, and this item will be an ACM file with extension .s. Give it a name. I will say main, and here it is. This is the file. To turn on the LED, we need to look at the schematic to see to which pin it is connected. Very quick, if you have Kyle, you have the schematic here under books. You have also a lot of documents, like example reference manual, datasheet. We will use all of this. So first, let's go to the schematics. Here it is, the schematic. On last page, I'm finding this LED 2, which is the green LED. I also see that it's connected to this SB21. So this is a switch bridge, and this switch bridge is a resistance that must be on your board. So if we are going to the user manual of the Nucleo board, on the bottom layout you have some resistance for these switch bridges. So you need to have this SB21 connected or bridged. So let me go back to the schematic, and from here what we are going to see, it will go to this D13, and this D13 it's on the front, this one, this pin from here, D13. But we are not interested about that pin. So we see that there is another switch bridge 42 that must be on your board, and if this is present, it will be connected to the PA5. This PA5 is the pin of your microcontroller. Now that we know that this LED is connected to the PA5, this means that we need to enable the clock for the GPIO A. We need to set the port to direction as output, and we need to write the high value to the PA5 line, to the pin 5 of the port A. Now I have copy pasted some code really quick to proceed faster with this video. So in here we define the stack size, heap size, we created the vector table. I only added 2 vectors, so the top of the stack and the receipt handler. Where you are going to find these vectors? Inside the Cortex M4 generic user guide. Open this, and here is the vector table. Here are the vectors, so I will only write code for these 2 vectors. So the rest of the vectors, I don't need them for this example. Now, as I said before, here is the clock enable for the GPIO A peripheral, and yes, we need to go to the datasheet. We have done that. We need to know that there are 2 types of buses, one peripheral and one high performance bus. Next, inside the datasheet to page 67, this is the memory map. Inside this memory map, the GPIO A peripheral is found on this bus, advanced high performance bus 1, which starts from this address, and the clock is found inside a register called RCC. So I'm scrolling down for that. Here it is. So we need a reference to this start address of the register. So that's what we have done in here. We need to go to the reference manual. So reference manual is this one. I have it already open. And from this reference manual, we need to know which bit enables the clock for GPIO A. And that is found inside this register. So I'm going to copy the name from here. Also, I have put the page number, so maybe go directly to the page number. Here is the peripheral clock enable register, and we see that it's an offset, so the offset is from the base address, so base address is this one, so that's why we need to add the offset. So this will be the register address, and inside this register address I shifted 1 to bit 0, so this is how the value will look after the shifting. And here is what it says about this bit 0. Bit 0 GPIO A N. So let's scroll down. IO port A clock enable. This bit is set and cleared by software. Value 1 IO port A clock enabled. So we have enabled the clock for our GPIO A peripheral. Next, we need the base address of GPIO A. This also from the memory. Let's go to this page 67. Inside datasheet, page 67, so this page, we need to find the GPIO A. So let's search for it. Here it is. So it is on this bus, and this is the address, the base address of the GPIO A. So this number, GPIO A base address, is like the one from the datasheet. So datasheet, and from this address we need to find the register for the mod, and this mod will say if the pin is an out pin or an input pin. So for this we need to go to page 186 in a reference manual. You made an idea how you are searching for these registers. So here is the GPIO port mod register for all of the ports from A to H. Also very important, we don't need to play with the port to initialize on the port A to 0, the reset value is A8000, and port B has this value, and the other ports are 000. Very important not to change the configuration, but only for what we are interested. So we are interested for PA5, which is model 5. So inside model 5, we have to write something. We have to put 00 if it's an input and 01 if it is an output. So this is bit 10. We need to put an 1 in here. This is what's happening. After we, from the base address, the offset, let me go back, the address offset is 0. So this has no offset. And on this, we need to shift 1 to position to bit 10. I created here some more symbolic constants. Here, the LED pin. So we need to access the output data register. And let's go to page 189. So here it is, GPIO port output data register. It has this offset, and for the output 5 is here. So we need to put an 1 in here, and the output will be on or active, and the LED will be on. So GPIO ODR, we take the same base address because it is the same. The offset is different here, and we need to shift 1 to position 5. But for this example, inside the assembly code, I will put a 0, and after that we will reverse engineer the hex file and put the 1 shifted by 5, which is value 20 in hex, to the hex file, and flash that modified hex file, and we will see that the LED is on. Now let's continue further. Now it starts the text area that contains code. It's of type read only. So either reset handler or main, they will both execute this line right here. So branch with link to system init. Now we are in system init. Here we can read the comments. It's very straightforward. We load the address value to R0 register, where you are going to find these registers also in generic user guide. Core registers, these are the registers. So when you are writing assembly programs, we are going to use these registers. So we load the address, the value of the address to this R0. Then what we are going to do, we are going to load the contents found at that address. So this brackets means load the contents from that address to this R1. Then we are going to do the OR operation like we see here in the comment. So this is what will happen. So we are taking this 1 shifted by 0 and make a bit OR operation with the contents found at that address. Do not change any of the other bits and store it back to R1. Next, we are going to store the R1 value to the inside this address, and this will enable the clock. This is straightforward. This will enable the direction. It will set it as an output, same as the clock enable. Next, we are ending the subroutine with this VXLR, and we will be back here, and we will continue to the next level, which is loop. And inside this loop, we'll go to this branch, turn on LED, and after that, branch back to loop. Let's see what this LED does. It will load the value of the address found inside this symbolic constant to this R0. Next, R1 will be prepared with LED on value, but LED 1 will be 0 for now. Next, we are going to store this R1 to the address indicated by R0. It will not turn on the LED, but we will modify the hex and we will turn on the LED by modifying the hex. And let's compile it. Let's make some settings here. So our internal oscillator is of 8 MHz. These addresses are okay. You can verify them with the datasheet. What else I want here? I want to create a hex file so I can modify it and turn on the LED. And inside the debug, I want the ST-Link debugger, and on the flash download, I'll also check in the reset and run. So okay, now I'll open up the camera for the STM. I will load the code. So verify okay, application is running, but the LED is not on because this symbolic constant has the value 0, doesn't have the value 1 shifted by 5, which in hex is value 20. Now let's modify the hex. I don't have the hex. Let me look again. Create hex. Okay. Build. Now the hex was generated, so here is the hex file. I will make a duplicate of it. So here is the copy hex. I will edit it with notepads to see that you can use any text editor. I want to open it. And let me see. Yes. So here is our program. This is how big it is. And let's discuss about of these lines. First line, it says that it has 2 data bytes. Next one 10, 10, 10, 4, 0. And this is also indication of the end of file. So this is the end of file and this is the checksum. Now let's get back to the first line. 0, 0, 0. This is the address, but in here this 04 indicates that this line is an extended address. So this 0800 is the 16-bit from a 32-bit address. So let me open another notepad. So this will be the most significant 16 bits of a 32-bit address, and in here are the other 16 bits of the address, so the least significant bits. This is the most significant word and this is the least significant word. So this is the first address, and you already see that these are the addresses of the flash memory of our microcontroller. We know what these are. Next, what this 00 indicates, it indicates that it will follow data code. So I will leave this to you as a homework to transform all of this data code back to assembly code. But for now, to speed up the things, here it is the LED on value. So in here we need to put 20. So 1 shifted by 5 means 20. But this is not enough because here is the checksum, and the checksum with this 20 will not be the same. So let's calculate first the original checksum. So let me show you how it is calculated first. So I'm going to take this line without the checksum, and what I'm going to do, I'm going to make pairs of each hex byte and make a summation of them. So now I'm going to copy this sum, and I'm going to open the Windows calculator. Here I have the calculator. I'm on the programmer, so you can select here, standard scientific programmer. I'm going to the hex. I'm right clicking on this space. I'm going to paste, press enter, and here is the number in hex of the summation. Now I'm going to apply the first complement. So the first complement means to reverse 0 with ones and ones with 0. So 1, 0, 1, 0. I'm also using this calculator. I can do this on paper also, but why not do it inside a calculator? So the result is AB4. I'm going to write this here, AB4. And after this sum and the first complement, you need to add 1. And the result will be AB5. And make a mask with FF. And the result will be B5. And this is indeed, it is B5. So now to turn on the LED, we know from the machine code that in here must be a 20. Now let's calculate the checksum for this 20. So that 20 will be here. I'm going to make like this. Control C, going back to the calculator, pasting the sum, press enter. So we have 56B. Now let's go to this bit toggling keypad and let's apply first complement. Once complement. So we have the result A94. To this A94 we need to add the 1 and it will be A95, and after the mask will be 95. So in here we need to put our 95. So with this 20 here must be 95. Now press save So you see, I'm using the notepad. Now I'm going to open the ST-Link utility. Here I have opened the ST-Link utility. I'm going to connect to the board. I'm going to the target program and I'm going to test objects and here copy hex. So this one, I'm going to open it, start the programming, and voila. So I think you already see that the LED is on. I'm going to point to it if I can. So here, LED 2 is on. So I made the modifications by reverse engineering the machine code and turn on the LED. If I'm going to flash back the original file, the LED will be off. Here it is. Now the LED is off. Thank you very much for your attention. If you like the video, give it a like, consider subscribing to my channel, and this is it. Goodbye.